Even if the sun's out in Florida or there's a nice breeze in California, the weather in the US is always doing something. But what happens when it just stops? I mean, when a normal week's forecast on the prairies or a mild winter day on the East Coast suddenly turns into something totally extreme, super persistent, and just completely out of left field, you check the forecast. Everyone checked the same app, the one with those nice, clean icons and that simple hour-by-hour breakdown. You did everything right. The model said a few inches of snow, just a dusting, a small annoyance on a cold Tuesday. You filled up the windshield washer, you grabbed some salt for the front steps. You trusted the algorithm. The official word beamed to billions of screens saying tomorrow would be fine. You knew the plan, and then the first flakes started to fall, and they just kept coming. That dusting turned into a thick blanket. That blanket became a wall of white. The whole city just stopped. 2 inches became 10. 10 became 20. Your usually quiet street, the one that forecasts said would be clear by morning, became an Arctic mess you couldn't get through. Your car? A frozen brick. The plan was gone. The forecast was a total lie. Just like that, the most advanced prediction network we've ever built got completely fooled by a cloud. But a small group of forecasters saw it coming. The old-school types who still look at paper charts, the ones who watch patterns, not just what's on a screen. They knew that storm wasn't just passing through. They knew it was settling in. Today, I'm going to show you how the atmosphere really works, the stuff the computer models miss. Seriously, where are you watching from? Tell us in the comments. I'd love to know where these weird weather patterns hit home for you. To get why that digital forecast on your phone can be so totally wrong sometimes, you gotta understand what makes it. For the past 40 years, weather prediction has quietly gone through a complete overhaul. We went from drawing with felt-tip pens on laminated maps to supercomputers crunching trillions of numbers every second. This is called numerical weather prediction, or NWP. And it's an amazing human achievement. Huge global models, like the American GFS and the European ECMWF, slice the whole atmosphere into a 3D grid. And in each little box of that grid, the computer solves physics equations, fluid dynamics, thermodynamics, radiation. It basically takes a snapshot of the atmosphere right now and pushes it forward in time, little by little, to make a forecast. It's a hardcore way to predict the future, and it's incredibly powerful. For everyday weather across places like the Mid-Atlantic, or just tracing a cold front over the Midwest, it works with an accuracy that would have seemed like science fiction not long ago. That's how you get the app on your phone. A clean, simple, boiled-down result from one of these giant model runs. It gives you a temperature, a percentage chance of rain, a number for how much snow to expect. It makes the future seem like it's a sure thing, a problem that's already solved. But there's a huge flaw built right into this system, and it messes up forecasts from Seattle to Miami and from San Diego to Boston. The machine has no gut feeling. It doesn't remember things long term. It only knows the physics inside its grid boxes and the data you feed it. It literally can't recognize a pattern it hasn't been programmed to see. These models tend to do what forecasters call climatology. They just want things to go back to average. They're built to keep things moving. A model run will almost always push a storm system along a predictable path from west to east, because most of the time, that's what happens in the continental US. It really struggles to figure out a system that just stops. If it sees a traffic jam in the atmosphere, its first instinct is to try and clear it out, to push the system out to sea in the next update. This creates a dangerous loop of false confidence. A forecaster looks at the GFS model. It shows the storm moving along. Then they check the European model. Same thing. Then the Canadian. Then the UK Met. They all show the storm moving out. And suddenly, there's a consensus. Not a consensus of actual people, but a consensus of computer code. A bunch of algorithms all heading toward the same, comfortable, climatologically correct, and totally wrong solution. They just back up each other's mistakes. The TV meteorologist reports the consensus, because going against it is a career risk. The app on your phone reports the consensus, because it's just an automated picture of one model run. The whole information system, from the National Weather Service to your local news, gets aligned around a future that just isn't going to happen. The machine is basically telling itself what it wants to hear. Meanwhile, outside the window, the real world, the actual world, is doing something completely different. It's getting ready to stop dead. The human forecasters, the ones who saw the disaster coming, weren't staring at the 1-2 hour video loop of the storm itself. They were looking at everything around it. They were looking for the jailer. The most common and really powerful jailer in the atmosphere has a simple, elegant name: the Omega Block. When you look at a weather map of the upper atmosphere, you're not seeing temperature or moisture, you're seeing pressure. Specifically, you're looking at lines of equal geopotential height. Think of it like a topographical map for the sky. The valleys are low-pressure spots where storms usually happen. The mountains are high-pressure spots where you get clear skies and nice weather. The wind, basically the jet stream, flows along these lines like a river. Normally, these high and low-pressure areas are always moving. They march across the map from west to east in a familiar parade that often brings front after front across places like Missouri, Ohio, or Pennsylvania. But sometimes, a high-pressure area gets so big, so strong, that it just locks in place. It becomes a mountain that the river of air can't flow over anymore. The jet stream has to go around it, flowing south, then north, then south again. On the map, this pattern looks really distinct. It looks like the Greek letter omega. Omega. That's the block. The high-pressure heart of the omega is like a fortress of sinking, warming, dry air. It's a literal wall in the atmosphere, sometimes thousands of miles wide, and it just won't budge. On either side of it, stuck in place, are two low-pressure areas. They're cut off from the main flow of the jet stream. They're trapped. A storm that forms or moves into the eastern low on the downstream side of the block has nowhere to go. The block to its west keeps it from moving east. The jet stream flow to its north keeps it from escaping northward. It's stuck in an atmospheric prison, and all it can do is sit there and swirl. And rain, or snow, for days, sometimes for weeks. Now, the machine, that numerical model, has a seriously tough time with this. The physics equations want that energy to spread out. The model really wants to weaken that high-pressure ridge. It wants to nudge the storm along its way. Every time the model runs, every 6 hours, it shows the block breaking down just a little further into the future. It constantly predicts an end to the pattern that just never happens. For the person living under that trapped low, whether in upstate New York dealing with endless snow, or the Pacific Northwest under constant rain, it feels like meteorological manipulation. The forecast keeps promising relief. The snow will end Thursday. Then on Thursday, the new forecast says, the snow will end Saturday. On Saturday, it says, the snow will lighten up on Monday. The model just keeps pushing the problem down the road, unable to admit it can't solve it. The pattern is just stronger than the physics in its little grid boxes. One of the most famous times this happened was in the UK in the summer of 2007. A huge omega block just plopped itself over Scandinavia. For the folks under the high in Finland and Sweden, it was an amazing, record-breaking summer of sun. But for the UK, stuck under the eastern low-pressure area, it was a disaster. A bunch of storms, completely cut off from the main jet stream, just cycled over the British Isles, one after another. They couldn't go anywhere. The ground got soaked. Then the rivers started to flood. The Severn, the Thames, widespread, horrific floods happened. And through the whole thing, the models kept forecasting the block would break down. They kept showing things going back to normal westerly flow. They were wrong, day after day. For almost 2 months, the pattern held. It was a harsh lesson in what automation can't do. The algorithm promised normal. The sky delivered disaster. An omega block doesn't just happen randomly. It's the grand finale of a huge atmospheric change. It all starts with the jet stream itself. The jet stream isn't straight. It wiggles north and south in big, continent-sized curves. We call these Rossby waves. When these waves are small and move fast, you get changeable, moving weather. A little rain one day, sun the next. But when these waves get really big, when their north-south wiggles become extreme, they can slow down and even break, kind of like an ocean wave hitting the beach. When a Rossby wave breaks, it shoves a huge mass of warm air northward, building a ridge, and a huge mass of cold air southward, digging a trough. If this whole thing is strong enough, the wave will basically flip over, cutting off the peak of that high-pressure ridge from the main flow. This creates the block. It's a self-sustaining bubble of high pressure that isn't being pushed by the jet stream anymore. It's pushing the jet stream. It's in charge. For a forecaster trying to predict snow for a city, this is a huge moment. Do you trust the model that says the storm will move off in 36 hours? Or do you trust the pattern you see on the upper air chart, the signs of a breaking Rossby wave that tells you the storm is about to get trapped? Do you trust the machine? Or do you trust your own eyes? The defiant forecaster, the one who earns their stripes by nailing the big storms, knows the block is the most important thing. Everything else is secondary. The exact temperature, the precise amount of moisture, those are just details. The first and most crucial question is, will the system be allowed to leave? If the answer is no, then you're not forecasting a snowstorm anymore. You're forecasting a siege. But omega blocks aren't the only way the atmosphere hits the brakes. There's another, even more stubborn pattern. It's simpler, but just as powerful. It's called a high over low block. Instead of the omega's symmetry, this one's a double act. A really strong blocking high sets up directly north of a cut-off low-pressure system. The high pressure to the north keeps the low from moving north. The east winds on the south side of the high keep it from moving east. The low is totally trapped. It can only sit there and spin, or sometimes actually drift slowly westward against the normal flow of weather. This backward motion totally freaks out the models. It's like watching a river flow uphill. The models fight it tooth and nail. A perfect recent example of this was the awful Texas freeze in February 2021. This enormous, super strong ridge of high pressure formed over the Arctic, linked to a messed up polar vortex. This high dove south, right over the central United States. Below it, a series of low-pressure systems and Arctic fronts were shoved deep into Texas. The high to the north was the wall. The lows were the prisoners. For days, the pattern was locked. Frigid Arctic air, usually stuck up in northern Canada, poured directly south and just stayed there. The models, even just a few days out, totally failed to grasp how long the cold would last. They kept trying to push the high pressure away. They kept trying to bring in warmer Pacific air from the west. They kept trying to go back to average. The state's power grid operators, relying on these forecasts, were completely unprepared for a cold event that wasn't just a quick spike, but a prolonged deep freeze. The consequences were tragic. The grid failed. Millions were left without power in deadly cold for days. The machine's failure to see the block, that simple high over low pattern, cost human lives. It wasn't a physics failure. It was a failure of imagination. The algorithm couldn't picture a Texas looking like Antarctica. The pattern, though, made it happen. So how do the best forecasters see these blocks coming when multi-million-dollar supercomputers totally miss them? They look for clues in places the models don't really pay enough attention to. They zoom out. They look for these long-distance connections in the atmosphere that set the stage for these traffic jams. We call these teleconnections. The atmosphere is wild and chaotic, but it has preferred ways of behaving. Rhythms, oscillations. One of the strongest is the North Atlantic Oscillation, or the NAO. The NAO measures the pressure difference between a semi-permanent high near the Azores and a semi-permanent low near Iceland. When this pressure difference is big, the NAO is positive. The jet stream is strong, straight, and blasts storms quickly across the Atlantic. Europe and the eastern US get mild, wet, and windy winters. But when that pressure difference weakens or flips, the NAO goes negative. The jet stream weakens and buckles. It gets wavy. And that waviness is what starts blocking. A negative NAO means a blocked-up pattern over the North Atlantic is likely. It means high pressure is probably going to build near Greenland. Forecasters call this the Greenland block. A Greenland block is basically the main engine for really brutal East Coast snowstorms. It stops any storm moving off the American coast from just sailing out to sea. Instead, the storm gets forced to turn north, up the coast, or just get stuck altogether, sucking in deep moisture from the Atlantic and dumping feet of snow from Washington, D.C. to Boston. The huge blizzards of history, the ones people still talk about, almost all have the fingerprints of a negative NAO and a Greenland block on them. Snowmageddon in 2010. The blizzard of '96. These weren't normal storms, they were trapped storms. Jailed by the Greenland block. An old-school forecaster who sees the NAO index dropping sharply doesn't just see a cold snap. They see the potential for a monster. They know the atmospheric prison is being built. Another really important teleconnection pattern is the Pacific North American pattern, or PNA. This pattern controls where those high-pressure ridges and low-pressure troughs are over the Pacific Ocean and North America. In its positive phase, a big high-pressure ridge builds over the western U.S., and a deep trough digs into the southeast. This pumps warm, dry air into the west, hello California drought, or really unusual heat in Nevada, and blasts the east with cold. A really strong positive PNA is another huge warning sign for a blocked pattern. So a smart forecaster isn't just looking at the 5-day forecast. They're watching these indexes, the NAO and the PNA. They're monitoring the planet's pulse. And there's an even deeper signal they look for. A signal that comes from the very top of the world, from the stratosphere. Something happened in the winter of 2018 that the standard models completely missed until it was almost too late. A huge area of high pressure built up over Scandinavia and Siberia, and this wave of unbelievably cold Arctic air just ripped westward across Europe. People called it the beast from the east. It snowed in Rome. It froze canals in Amsterdam. It shut down the United Kingdom. It was the kind of cold that just felt broken, ancient. And it didn't start in the troposphere, the part of the atmosphere where our weather happens. It started 30 miles higher up, in the dark Arctic night, in the stratosphere. Every winter, a massive, swirling mass of west to east winds forms in the stratosphere over the North Pole. This is the polar vortex. As long as that vortex is strong and stable, the coldest air on the planet stays locked up where it belongs, over the pole. But sometimes, that vortex gets hit. Big atmospheric waves from below, the same Rossby waves that organize our weather, can shoot upwards into the stratosphere and break, smashing into the vortex. This process quickly moves heat and energy into the polar stratosphere. The vortex slows down, gets unstable, and can even start spinning backward. The temperature in the Arctic stratosphere can jump by 50 degrees Celsius in just a few days. This is a sudden stratospheric warming event, an SSW. And it's the most dramatic thing that can happen in the winter atmosphere. A forecaster who sees an SSW occur knows that a clock has just started ticking. The effects aren't immediate. This disruption, this huge blob of warm, high-pressure air, slowly drops from the stratosphere down into the troposphere over 2 to 4 weeks. When that signal finally arrives, everything goes crazy with the weather below. The jet stream shatters. Huge blocking highs form all over the place. The Arctic basically opens its doors, and its air pours out into the middle latitudes, hitting states from Montana to New England, and sometimes diving deep into the south. The beast from the east was a direct result of a big SSW that happened weeks earlier. A small group of long-range specialists and academic forecasters saw it coming a month ahead. But the operational models, the GFS, and the Euro just wouldn't believe it. Their physics couldn't handle the signal coming down from above. They kept showing normal west-to-east flow, even as the real world was building one of the most extreme cold blocks in modern European history. This is what the masters know. This is the inside baseball. The guys running the phone apps are arguing about whether it'll be 2 degrees warmer tomorrow. The real pros are watching a temperature anomaly 100,000 feet over the North Pole that won't hit the surface for another 3 weeks. They're playing a totally different game. Let's be clear about what this doesn't mean. It doesn't mean every SSW event leads to a record-breaking storm. The connection is complicated. It's about probabilities, not guarantees. But it massively increases the chances of a really impactful, blocked, and long-lasting winter weather event. It stacks the odds. For a power company in Michigan, a water utility in Arizona, or a transportation department in Colorado, knowing an SSW has happened is a super important strategic warning. It's the signal to get the salt ready, to have linemen on standby, to prepare for a siege, not just a quick fight. The fact that the main models don't properly include this stratospheric signal is one of the biggest and most dangerous blind spots in modern forecasting. The machine is looking at the ground floor when the real problem is starting on the roof. It's like trying to figure out why a building is falling down by only looking at cracks in the lobby wallpaper. You're missing the core issue. You're completely blind to how big the threat is. The human forecaster, the analog resistance, knows you have to look up. Way up. So when all these things come together, a stuck omega block, a negative NAO, the signal from a recent SSW, the pattern just locks in. This is when a winter storm stops being just a storm and becomes a truly historic event. The impact on the ground is relentless. For the first 12 hours, the city usually handles it. The plows are out. People get home from work. There's a bit of excitement. By 24 hours, the excitement's gone. The snow is still coming down just as hard. The plows can't keep up. The side streets disappear. Main roads become super dangerous. Businesses close. This is when systems start to fail. The long, heavy precipitation really tests infrastructure. Flat roofs on commercial buildings, designed to hold a certain amount of snow based on average weather, start to groan under the weight of a stuck storm that's anything but average. We saw this with that Buffalo lake effect snow in November 2014. A super localized band of lake effect snow, fed by the warm waters of Lake Erie, just set up and refused to move. It was trapped by the larger steering currents. Some areas south of Buffalo got over 7 feet of snow. 7 feet. Roofs collapsed everywhere. Warehouses, supermarkets, homes. The community of Snowbelt, an area proud of handling snow, was brought to its knees because the storm didn't just pass through, it stayed. After 48 hours, all sorts of other problems start popping up. The supply chain breaks down. Trucks can't get into the city. Grocery store shelves start getting empty. Pharmacies begin running low on vital medications. The power grid, which might have held up fine against the initial wind and ice, starts to fail from 1,000 tiny issues. Transformers blow. Tree branches, heavy with feet of snow, snap and take down lines. Repair crews can't even get to where they need to be because the roads are impassable. This is what we learned from the Texas freeze. The first shock was the cold. The bigger problem was the infrastructure's inability to handle it for so long. A power plant fails. That cuts power to a natural gas compressor station. That cuts off gas to another power plant. The whole system just eats itself. All because the initial forecast didn't just fail to tell us how bad it would be, but how long it would last. It totally underestimated the power of the block. The risk isn't just the snow. The risk is that it gets stuck. The risk is time. A modern city can survive almost any weather event for 24 hours. But very few can survive a high-impact event that goes on for 5, 6, 7 days. The system has no wiggle room, no resilience. It's designed for the normal, moving weather the models promise. It's basically unprotected against the storm that gets stuck. The human cost of this failure is huge. It's not just annoying. It's drivers stranded and freezing in their cars, whether in Montana or North Carolina. It's house fires from people trying to stay warm, using dangerous methods in Oregon or Arkansas. It's heart attacks from shoveling incredibly heavy, Wet snow for days on end, from Minnesota to Massachusetts. The official death toll of a storm often misses these ripple effects, but they're absolutely real. They're a direct result of an atmospheric pattern the machine refused to see and the public was never warned about. Now, something has started to shift in the weather world. There's a growing understanding of this model weakness. The European Center for Medium-Range Weather Forecasts, home of that famous ECMWF model, has really invested in trying to get better at handling blocking patterns and their connection to the stratosphere. They're trying to teach the machine to have a better imagination. They're building probabilities into their forecasts, trying to signal the risk of high-impact, low-probability events instead of just spitting out a single definitive snowfall number. This is a step away from false certainty. It's an admission that the future is uncertain, and sometimes the riskiest path is the one the model says is least likely. But this is a slow burn. It's happening in research places. It hasn't really made it down to the app on your phone yet. The public-facing tools are still selling the illusion of certainty, because certainty is what people want to buy. It's more comforting to be told you'll get 3.2 inches of snow than to be told there's a 70% chance of 1 to 4 inches, but a 10% chance of 20. The first number is easy. The second makes you actually think, to weigh risk. The system is designed to give you the easy answer, the path of least resistance, just like the models themselves. So what can you do? You, the person on the ground, who has to deal with the fallout of a messed up forecast, whether you're in the desert Southwest, the rainy Pacific Northwest, or the snowy Northeast. First, learn to spot the signs of a high-risk pattern yourself. You don't need to be a meteorologist. You just need to know what to look for. When you hear the TV weathercaster mention a cutoff low or a blocking high, listen up. Those are code words for a storm that might get stuck. When you see a forecast for a big winter storm, don't just look at your own town. Zoom out. Look at the whole national map. Do you see a big, sprawling area of high pressure just sitting north or west of the storm? That's the jailer. That's the block. Be super skeptical of any forecast that moves a storm quickly out to sea when a massive blocking high is right in its path. Second, pay attention to how they're talking about uncertainty. If a forecast from a reliable source, like your local National Weather Service office, starts talking about a wide range of possibilities or low confidence in the storm track, they're telling you the models are struggling. They're telling you the pattern is tricky. That's a sign to prepare for a worse outcome than the official number might suggest. The best meteorologists tell you about this uncertainty. The bad ones just give you a single number with fake confidence, right up until it's completely wrong. This whole thing is about recognizing patterns over blindly trusting models. It's a fight against the false certainty the algorithm gives us. That digital consensus makes things sound simple and neat, but the sky is messy. It's real. It's wild. The machine wants to predict a number, but the real world is telling a story. And the stuck storm is a story of being trapped, of a siege, of endurance. As long as the jet stream can wiggle and break, as long as high pressure can build a fortress in the sky, the risk of a storm that just won't leave will always be here. The quiet effort of human forecasters who know how to read the patterns, not just the code, is the only thing truly standing between a city that's ready and a total disaster. Have you ever been totally stuck by a storm the forecast just missed? In Florida, California, or anywhere else? What's the worst forecast screw-up you've ever seen? Tell us your story in the comments below. Hit subscribe, and I'll see you in the next one.